and that's who our supervisor is Todd, the program director for the CAD department, and this is one of his suggestions on how we can make this available. So, all right, well, we're going to get started here with what we wanted to talk about today, which was chapter 17 in our electricity for HVAC book. Electricity for HVAC. Chapter 17 was, what was the name of it? Electrical drawings? Electrical diagrams.
Understanding electrical diagrams.
Yep. Okay.
Page 308.
Yes, sir. Yes, sir. So we're going to get started with the PowerPoint here, talk about what our Uncle Ken wanted us to know. Well, yeah, that's what that means. Please do. I would like to be referred to as Uncle Brian. So, however you want to work that out. All right, let's get back on topic here. We are recording right now. So, okay, electricity for HVAC, understanding electrical diagrams. So, we're going to do some diving in here. What do you guys think we're going to talk about today? Electrical diagrams? All right, all right. What our unit objectives is and what we will have accomplished by the end of the day is to draw and identify symbols used in HVAC and refrigeration schematics, describe the different types of electrical diagrams, and discuss 2 reasons for using electrical diagrams. We're also going to describe 2 reasons for developing an electrical schematic and describe the steps in developing an electrical diagram. So this was something that we should maybe pay attention if we haven't got our assignment down yet. An electrical diagram is an organized group of symbols with interconnecting wires. Electrical diagrams help the technician make sense of what's happening in an HVACR system. They are the road maps through the system. So when we're talking about the electrical world, these are our Bible. These are what we want to be having our hands on. This typical ladder diagram, the upper section is the high voltage section, and the lower is the low voltage section. We see this symbol right here. What do we suppose this is? Absolutely. Absolutely. What's the voltage on the primary side, do we think? Yeah, I would say that's definitely a possibility, though my only hesitation would be that usually when you see an L2, that's another leg of 120, so a different phase. From what my experience is in schematics, usually you'd see on this side an N if it was a 120 volt circuit to indicate a neutral. There is sometimes where that crosses over where L2 and N mean the same thing, but without having that indication. What's that?
There seems to be a lot of videos as to
yeah, usually it would be indicated. You know, that's the long and short of that is it will be indicated with if this was actually on a unit and we will check today, we will see what this voltage is between here, and it'll probably have a little indication somewhere that line to line voltage is either 120 hot to neutral or 240 phase to phase. So diagrams are the road maps through that. Think of wire connections as the roads through the electrical circuits travel. The roads through the electrical circuits travel. That's a weird sentence, huh? Think of the wire connections as roads through the electrical circuits travel. Okay. Yeah, no kidding. I think what they're trying to say is let's imagine that the wires are the roads that the circuit is going to travel.
Why did you say that? I think that that's circuits.
That's entirely fine. Maybe you could think about it as water pipes for all I care. The symbols, like landmarks on the road, are used to identify the components of the electrical system. You are learning new language. You are learning a new language that uses electrical symbols instead of words. In some cases, there will be some cases where we just write in what we're talking about. Whoops, wrong direction. So even though these electrical symbols are common, they are not universal in the United States or worldwide. And that's something that I definitely want to highlight with you guys. Is that these may very well be what you are expecting to see in your world. But coming from my point of view, a lot of this stuff doesn't apply. This is common. That's a common thing that we see. The ground book, these are common, normally open, normally closed. That's usually a fairly common one, indicating you have a contact from a relay somewhere. I wouldn't necessarily agree that that is a relay. I would think that that is a contact, and I think that's what it's indicating there. Transfer, you guys see that in your stuff, in your past? See transfer? I don't think so either. This is something that's pretty important for us right here, the connections for the connectors, conductor connections. A lot of times, at least as far as I can tell, we're going to have a dot there. I do have a couple examples of what we're going to see where there isn't a dot, then we just assume that the straight line is going to continue through the circuit. Okay, it's definitely something that you can do. Okay, resistors. We talked about these the other day. That's the symbol that you guys are going to use for them. I've also seen them, resistors in your guys' world, just being a rectangle with two lines coming up the center with the resistor road in there. Oh my word! Vibrate it, please. Thank you. Okay. All right. Now that let's see, what else do we got to talk about? Thermocouple. I don't know how many of them you're going to see out. You're going to see a buttload of these. Transformers, you'll see them out there a lot. Of course, a lot of thermostats over in your world. Pressure switches, flow switches, these are pretty neat. The differences between the between this flow and this flow. Here's something important to remember too, is the fuse, is the difference in the fuse. That's pretty much all we really need to. Pilot light, there's several different symbols for a pilot light. I think we touched a little bit on that. Maybe not. Okay. You will learn how these symbols are used to develop circuits that operate air conditioning, heating, or refrigeration circuits. You will also see that identical circuits can be drawn in several different ways. You will find out how to develop an electrical diagram if one does not exist. I cannot tell you the number of times that I've been called to work on something electrical, and instead of being able to generate a print, you just don't have anything, and you just got to go after it. You break out your meter and you start following out wires and making a circuit up. And that's where having a little piece of paper and a pen handy is something that's almost a necessity when you start to break up your own circuits. So in summary, this unit covers basic types of circuits, electrical symbols, and electrical wiring diagrams, and how to develop these diagrams. Symbols represent a component in an HVAC235 circuit. Symbol list next is the most common symbols used in this textbook and in your industry. We don't need to spend any more time with that because we're going to do this. So right here, what can we tell just by looking at this? So drop on temperature. The switch right now, what is the state that the switch is in? Okay, it's an open switch that's going to close when we get the temperature that it requires. So the symbol represents a heating thermostat switch. So the next symbol is going to be the opposite of that. So this switch is normally closed right here, and then it's going to open whenever the thermostat reaches whatever temperature it's set to reach. So, everybody clear on that? Casey?
Yeah.
Okay.
I was just thinking, would that normally be on one since it's on a certain side?
Say that again?
How I've seen it so far is this normal?
Is this a normal symbol?
What I'm saying is, because it's on the bottom side of the contact,
This is over here.
is that a lower temperature, or lower temperature?
What do you guys think?
That's
I would
what I've
say,
seen.
sure, and that may be the case.
All lower.
Same.
Close on rise.
So the note that I have on this is that an increase will close this switch. That's the note I have. This switch looks closed to me.
And a decrease will open. It's just the same thing.
An increase will close this switch. So a decrease will open this switch. All right. What's this is the normal state that this one is in.
That's what I'm saying.
Then what's the question? No, I want to know. I want to get you on the same page.
I asked the question. Still about where it was.
I guess maybe I'm not understanding what you're confused about then.
I'm not confused. I was just wondering if that's what the standard, or if there was a semi-standard, I guess, because a lot of these are very standard.
So I would say that's a standard for this particular application. What I have right here is a decrease in temp will close the switch.
Yeah.
Okay. So that's the standard for a normally open decreasing.
What I'm saying, if that arm was on the lower side, that would be an increase in temperature close.
I think so. I think you're right. I don't think you're confused. I think you're right on.
Yeah, that's what I was getting at, if that was a normal thing.
Yeah, I think you're right. I think, yes, that is normal. So let's talk about this. Symbol representing the symbol on the left represents the relay or contactor switch. Different symbols are used for different coils. I've seen a gob of these, the circles, and I've seen a gob of these for your guys' contactors. I've seen a gob of these in my world. These are used a lot for solenoids. Solenoids is basically the same thing. It's and then this whole setup here, that's somewhat uncommon, I would say. Maybe not in an HVAC drawing. I think I've seen those where they have this coil right here, and then they actually bring the wires to the actual contact and demonstrate, hey, look, these wires are actually going right here. I think I've seen that before, looking at your guys' stuff. But this is a pretty standard symbol for a coil here. Right, Daniel? Yeah, that's what I thought. What do we got here, Jason? I agree. This is a pressure switch. As the pressure increases, we're going to move the rod to the up, and the movable arm is going to open up the contact there. Whoop. What do we got here, Daniel? I agree. This looks like a close-on rise right here. As the pressure is going to increase, it's going to move the switch arm up and close the old contactor there. Jimmy, transformer. If you're being tested on it. Oh, don't worry about that one then.
Remember use technology.
Yeah.
Copy and paste, I'd be okay with that. Yeah, that's tough. Here's what I want you to do. I want you to open up paint. And I want you to use your little pencil and draw it in paint and then import your picture into Word. No, I don't. No, I don't want you to do that. No, I feel that I'm confident that you guys are able to draw a transformer. I feel like I can say that about this group. that's not too bad of a thing to draw either. What do we have here? We have another symbol for a transformer. The transformer windings are not illustrated in the wiring diagram as shown here. So what do we see as the difference between this? It's just saying that the windings are there. I feel like everybody's probably pretty confident with that knowing that you're having an iron core on that guy, and that's obviously a step down from your 240 volt primary to your 24 volt secondary. That's what we were doing earlier today. As you can see, if I draw a ring up here, here's a symbol for a single phase compressor motor. The symbol is the single phase blower motor and compressor motor. The windings are not illustrated in the wiring diagram shown here. What do you suppose is going on? How come we have this one out here, but we have up here is still inside the circle and down here isn't? Yep, I like it. I like where your head's at there. Just how the symbol was designed, why there was only one wire poking out. So, here's a split phase motor, and as we see on this guy, we have, so once this hooks up to our wiring diagram, we're going to have a hot coming here, either another hot here or a neutral here if it's a 120 volt, and then down here, whether it's a high speed or low speed, we'll either have another hot coming here or whatever this system requires. But we have, each one of these has a different spot to land on for the wire. So circuit types, complete circuit. A complete circuit has a path of electricity. That electricity can flow through from the source to the source to the source through the circuit. It also is known as a closed circuit. If it's an open circuit, then we're not going to do anything because the electrons don't have a way to travel back home. And they're not too good for their home. The simplest complete circuit includes a power supply, a load or resistance, and interconnecting wires. Here it is, fellas. Complete circuit right there. So we have the 120 volt scenario here where we have the hot coming through, your 120 volt wire coming through, going through the load of your heater and returning back to the, in this case, wall outlet on the neutral. Here's another pretty much same drawing of that, except for instead of a heating element, we're just going through a coil of motor, which are essentially the same thing. They are a resistance to the flow. Whoop, wrong way. Nope, maybe not. A series circuit has the same current flow at every point in the circuit. If there are two loads in a series circuit, the current flow will be the same everywhere in the circuit, but the voltage will be divided across the loads. Series parallel circuits. Jimmy, you remember that, don't you? Okay. Daniel, remember series parallel circuits? A little bit? Been a long time? Yeah, that was all the way back in first semester when you were out there on the boards. Yeah. Do it learning by yourselves. If there are two equal loads in a series circuit, the voltage drop, measured voltage across each load, everybody happy with that? Like if we have two resistors in the circuit that are in line, the voltage drop across each load will be the same if they're the same size. If they're not the same size, then the voltage drop will vary depending on the resistance. So if we have more resistance, then our voltage is going to change proportionately to that. So let me get a little drink here. All right. So series circuits with some voltage drop. So the following example I'll pull up after this is an example of voltage drop across loads. The series circuits, the current stays the same. So in this case, multiple resistors in series are additive. So resistor 1 plus resistor 2 plus resistor 3 equals resistance total in this circuit. Here it is. Here's the hard circuit. Yep, it's pretty simple layout we got going on here. We're sending 240 volts out across two 12 ohm resistors in series. Jason, what's our total resistance in this circuit? 24 ohms. So when they're both the same size, we're going to have equal voltage drop across them. Everybody square with that? I think so. I think so. I think you've spent enough time with that. Parallel circuits on the other side of the spectrum are arranged so that the power source is the same across all loads. So what that's telling me is that current is going to be the same through everything. Current flow through each branch will depend on the resistance of the load in that line. Total current flow equals the sum of the amperage draw on each branch. So this is similar. This is the opposite of voltage in a parallel circuit. So where we're going to be able to, we could do this equation right here in a series circuit. Voltage drop total would be voltage drop across resistor 1, 2, and 3 would equal voltage drop total in the circuit, which should equal our total voltage. In this case, we're going to have our total circuit, our total current circuit, and it's going to be about the same, kind of the same series of addition and subtraction here. There is the difference that I added here between the two, and that's how you figure out your resistance total. The total and individual circuit current flow through a parallel circuit. Total and individual circuit current flow through a parallel circuit. What do you need, buddy?
I'm looking for a port.
A port and a storm.
Yeah. I don't know. I'll figure it out.
Okay. So, and then here's how we're going to figure out total resistance in a parallel circuit. Everybody remember this formula? Resistor 1 over 1 divided by 1 plus resistor 2 over 1, and then resistor 3 over 1, and then the reciprocal of all of that. Everybody remember that? You didn't learn it. We're going to learn it.
Okay. Let's go in that deep. This drink wasn't very inviting to that out, but was it? No. Of course it's all concrete, so yeah. Yeah. Water obviously, unless anything to spare. All right, so I'm gonna pull this guy up here. We'll just spend a minute learning this. Okay, so our formula for resistance total in a parallel circuit, so R T in, let's see, parallel is R1 over 1 plus R2 over 1 plus R3 over 1 with the reciprocal. So let's see, what is our example here? One more on down the line. Is it giving us anything? It's telling us 15 amps. 45 amps total in this circuit, and we're dropping 15 amps across each one. You guys see that okay? Good enough? Yeah. All right, so let's draw this circuit out. Wrong symbol. Here we are talking about electrical symbols. And I'm drawing the wrong one. All right, so what we can do here is we know that we're gonna have 1, 5 here, 1, 5 here, 1, 5 here, but we don't know what the resistance of these guys is, and we're going to assume that they're equal because we have an equal amount of drop across them. So we have 45 amps here. Do we have a good idea of what do you suppose our voltage is here? What are we going to assume that it is? Jason, you agree with 240? We got L1 on top and L2 on the bottom. L1's kind of cut off with the learning pyramid. Yeah, that's what I think too. So I think we're going to do 240. So what do we have to have in order for us to find the resistance of a circuit? We have to have voltage, and we have to have, in this case, current. So we have voltage in I, voltage current equals R. I don't know if that's the exact thing, but we're going to find out right now. Let me get off of here. And I'm going to cheat. Look at this little deal here. Maybe. Where'd it go? Booyah. Ohm's law calculator. I'm going to pull this down. There you go. Sweet. So I think we're going to want to find some resistance, right? Oh. Come on, come back down here. What's happening here? What's happening here? What's happening here? Man, we're really having struggles, aren't we?
You're talking about me, other people have issues too.
You're really causing me some trouble here.
I just say I use it. He just came in here and fixed another guy.
You didn't fix anything. You made it worse. Okay, well, all right. I apologize for that. We can move on without it. We're going to change this to make it easy for us, though. Well, just give me the reason. What is it? 7.0588. I think it's like do we have an actual Ohm's law calculator or some wheel in here? Lord have mercy. Maybe we can at least get that up. Lord have mercy. So what we're going to do is we want to find out what R is, right? So we're going to take our voltage divided by our current. Jimmy told us that our total resistance in this circuit is going to be, hey, look at that, I drew it out right, just on a whim. So 240 divided by 45 equals, that's good enough, 7.05 ohms in this circuit. That's what RT equals. So now we have to figure out this the opposite way. going backwards. Man, I wish I had. Does anybody have a calculator
I got 3.
per one? I'm okay with that because I think that's about what. Talk about that. Let me calculate it too.
Yeah.
What in the world is going on? Thank you, sir. Let me get on the same page here. I didn't, man, that's, okay. All right, so 240 divided by 45 equals 5.3. I got that same thing. Jimmy was pretty convinced that he gave us the right answer, wasn't he? Yeah, yeah. Okay, so 5.3 is what our RT is in here. I'm gonna get rid of that. Now we have to go about this the opposite direction from the formula I have. So we have RT, but we don't have what the individual resistors are. So we know that the total of this R is going to be 5.3, and we just have to plug this into the formula backwards. So we got to do some algebra there. Who wants to do that? 5.3. You think that's what it is? I thought that they were usually higher. I thought the reciprocal of this gave you a lower value. A lower value than all three, like the individuals. Yeah, I think so. Let me see where my number is. Divided by 1. Damn it. Is there a reciprocal on your phone? The reciprocal version on your phone? I know on the old Texas Instruments 35 there wasn't reciprocal. TI 35, yeah, that's the one.
Oh, this is TI 30.
Let's see what we're working on.
What are we doing?
We're figuring out what each individual resistance is. So that's what the resistance total is in our circuit, and we're trying to use that number to get down to what each individual resistance is.
So they say 5.3 divided by.
It's going to be the reciprocal. Let me find the reciprocal. There was a button on 35 that was just the reciprocal. Because it's lower than what it would be if you just take 5.3. Got it on here, doesn't it? Talk about the 5.3. Well, let's try it. Let's try one. If that's not what we suspect, let's plug that in here because I think that it's actually going to go the opposite direction. What did you think it was, Jimmy? 1 point something?
1.36. I'm not sure.
All right. Yeah. That's okay. We don't have to be sure. We're learning. We're learning as we go here.
Man, I can't remember what the reciprocal is either.
15.3 divided by 3 is 1.7.
The thing that we're having the trouble with here, I think, is that it's not actually divided by. It's the reciprocal, and that's different than divided by. And dang it, I wish I would have known we'd have gone down this road today because I would have brought the dang calculator that yeah, the resistance, so this is R1. Resistors in parallel. Yeah, what's the reciprocal button on here? You remember that? Is that it? That might be it right there.
Yeah. No, wait.
Okay. Let me try it.
No, it would be X1.
Yeah.
Oh, that is.
Okay. Let me pull this up for you guys to see.
Okay, so when I got, this is the reciprocal of 5.3 right here, this number. This, where did it go? Right there. Yep.
So if I go here, 5.3, that one is 0.18.
0.18. Man, I feel like we're getting kind of far away, and I think we should have used different numbers here.
So 15 is your resistance.
15 is the amps. That's the amps. Yep, that's the amp draw across each one of these. Because in a parallel circuit, amperage is always the same.
And then so your total resistance is 5.3.
And that's what we got off of this 240 divided by 45.
And then so the R1 plus R2 plus R2.
That's what we're solving for right now. So I want to change this just a little bit to where we get actual results out of this and they're nice square numbers. So we're going to change this from being a 15 example. We're using 24 volts, so let's just do 24 amps.
The one over the total, and that is like
It'll all make sense when we get to the end here, I promise. So our resistance total will be 10. So 10 ohms from here.
your reciprocal should be 0.1.
I'm thinking here. Wasn't expecting to cover parallel circuits today. Was expecting to talk about electrical drawings. So let's do this. 1 0 1 0 1 0. I want to get away from where we're at right now, and I don't want to know what the amps are. I want to know what the individual resistances in the circuit. So this is the direction that we're going to switch, and we're going to go just because this is the way that I really remember how to figure it out easily. Huh? Not necessarily. 240 volts in, and we have 3 10 ohm resistors. So our thing here is R1, so R1 equals 1 0 reciprocal plus R2 equals 10 over 1 plus R3 equals over 1. And then this whole number reciprocal again. So how we're going to go about this?
So I found all of the like test generator questions
Sweet.
for both the second and third edition and the test generator.
Right on.
When you want those, I have them on my computer whether it's available through IRC in person when you set that up. But I can give them to you before that.
Okay, we're going to have a test Thursday, so I'll come visit with you tomorrow. So let's just do it here. Let's work it out together. Okay. So 1 0 reciprocal, which is 0.1. So we know that this is how the equation is going to continue. So R1 equals 0.1 plus R2 equals 0.1 plus R3 that we already know equals 0.1. So it's going to be RT equals 0.1 plus 0.1 plus 0.1 over 1. Yes. So it's going to be 0.3, the reciprocal of 0.3, right? So we got 0.3 reciprocal. So that's how much our resistance total is going to be in this system. So now going back the other direction, when we had what we had over here, let me get rid of this. What do we have initially? We had amps and we had 5.3 ohms. So, and that was RT. So what we wanted to get was the reciprocal of that, right? We would take the reciprocal of 5.3, and then we would divide that by, we would 3 equal parts of that 0.18. No, I don't think you would divide it, right? Or would you? Of that number? Yeah, that might be it right there. That might be the stuff. So, exit. 0.56. That's a really small resistance. So what do we got? 5.3 reciprocal. Let me think for a minute.
I thought you wanted to do the reciprocal and then divide.
Divide this by 3 equals then the reciprocal of that. That's what I think that should be. The resistance across each one of those. It should be 15.9. Let's figure it out if it works. So we said that we have 45 amps down here for IT, current total. 45. And we know since this is a parallel circuit, across each one of these, we're going to have an equal. And since these aren't equal, even though that's not the case most of the time, we're going to have 15 here, amp drop, 15 here, and 15 here. Now what we don't know is what the resistance is, but we figured out what resistance total is by doing V over I. V over I equals RT, and we decided that that equaled 5.3. So now we have what our RT is, and we just have to plug that back in to this system over here to get us where we are on the calculator right here. So first thing that we got to do is we got to take 5.3, that's a shitty 5.3 ohms, and get the reciprocal of that. So over 1. And that brings us to that 0.18, right? So that equals 0.18. I believe that's what we got, right? 0.18. I can go backwards if we need to. So, bam, times 3 equals 0.18. That gets us to this point. Now we know, since we have 3 resistors in here and we know that they're all equal because they have equal current drop off of them, that we're going to be able to take this 0.18 and push it up into 3 equal sections. So 0.18 divided by 3 in this case equals 0.06. So let's see what happens when we hit the divide. 5 by 3 equals 0.06289. 0.06. Yep. So now we have what all 3 of these, the reciprocal, we don't have the actual value, we have the reciprocal value. So we still have the reciprocal them again. Now what we think here is we think we have the reciprocal of 0.06, 0.06, and 0.06 over here. So over 1. So now to finish off this problem, we have to come back at the reciprocal of those 3. And we can figure that out just by hitting the old reciprocal button right here. Where's that? Right there. And that's going to give us our 15.9. And I'm fairly confident that that's where we should reach. And see, and what I'm wanting to illustrate to you guys on this is that the
the total resistance in a parallel circuit, RT, is less than the individual resistance, even of the smallest resistor, less than R1 or R2. So the combination of those is going to bring the whole unit down. Everybody clear on that? I'm surprised that you guys didn't do this, and I wish I would have had your first semester, because we would have. Because you guys may very well see this. You may very well see a load in parallel. Let's call it that. A load in parallel somewhere. And you may need to figure out, especially let's just say these three are the coils inside of a motor. And one of these coils, yeah, let's see, are those in parallel though? No, not really in parallel. Yeah, definitely coils in a heater. That's a great example. And one of these heaters, they all should be equal, because you're expecting to put equal heat out of every one of them. But one heater's drawing 20 amps, one's drawing 8 amps, and the other's drawing 12. So you can tell, oh geez, I have some stuff happening inside of my elements here. So everybody got that? Good enough? Good enough to move on? All right. I definitely wasn't expecting to sideline us there, but I'm glad we did for a minute, just so we can refresh my memory and get you guys a little bit of information there. Cash is going to miss out on all of that. Sick kids. Okay. All right. Let me go get the light here and get back out.
I'm gonna find that.
Okay, back at it. Okay, I think we've exhausted everything there is to exhaust about that particular circuit. So let's move on a bit. You guys, what's the same in series circuits? What's going to be the same throughout? Current drop is going to be the same throughout a series circuit. Voltage drop will be the same in a parallel circuit. Let me think about that for a second. Yeah. The voltage is going to be the same for each one of these here, here, and here. But the current will be different, because you see the relationship there? All right. And then you have these old devils, series and parallel circuits. It says here that these are the most common type of diagram for you folks. So I'm glad we spent some time on that. Here's a simple ladder diagram of a series parallel circuit. Shows the parallel loads in series with switches that control their operation. What is this symbol right here? I don't know. It looks kind of like a capacitor to me. It does kind of have the hook on the outside there. Yeah, 17-1.
Yeah, I call it.
I think so too. I think that's a cap. But what we do, it does, what it's showing here that definitely is in parallel is the fan and the condenser motor, the condenser fan and the indoor fan motor with that contactor there, that contactor being the thing that pulls in the switch. Yes, my friend. Where's the series circuit on there? Yeah, I guess you could call the thermostat and the thermostat and the limit switch. Those are definitely in series there. And they're getting fed by the low voltage side of their transformer, I would assume. Maybe not. I bet you that's the high voltage side, because it is hooking on to the high voltage wire there, so. The compressor's in series with, what'd you say? Yeah, I don't know. It looks kind of like that spot right below, right there on the top. It looked like maybe the R wire, R or S maybe, the one right above the S. That looks like that's telling me that it's in parallel with something. Yeah. So an open circuit means that there is a breaker or a break or an opening in the wire or load that stops the flow of electrons. The following image shows an open circuit with in series with a fan motor. A common way to open a circuit is with the use of a thermostat to open cooling, heating, or refrigeration circuits when they are not required. So there's your open circuit. Everybody's got some groundbreaking stuff to learn about. The switch being open means an open circuit? Okay, me neither. Short circuit. A short circuit has a voltage going to ground or around the load. The word short means the voltage is taking a shortcut around the load. All right. A short circuit does not need to be a direct short to ground or a routing of the voltage around the load. For example, a condition which is the load has a very low resistance, that is a short circuit condition. A load that is 10 ohms but actually a load that is 10 ohms but is actually 2 ohms is a short. This is something that you'll definitely see when we start looking at wire, our coils. It's possible to have, if a coil heats up, it's possible for the internal windings of the coil.
What they're trying to say is that it's supposed to be 10, but it's actually 2.
Yes, that's what they're trying to get at. Yeah, it's sometimes rough, and we're going to see a graphic here that's going to make you guys giggle too. Everybody need a break? Anybody need a break? Okay, let's have it then. It's been about an hour. Let's make it quick if you don't mind, though. Oh, you're not taking any medication.
It's all right. I already.
Thank you.
Yeah.
That'll dramatically improve my ability to focus.
All right. This is a long one. I think there's 100 slides to this one. We're gonna
That's a long one.
We're gonna start breezing through though. A lot of them are like the next one after this particular guy's only got one sentence. So I have no problem talking as you haven't. Sometimes it's probably hard to follow, but I can make sound.
I don't know who does these slideshows. Even 50 slides is a lot of slides per slideshow.
Yeah. Well, and the way that this was lined out, I personally would have probably rather saw this particular what we're doing today at the beginning of the semester. Like it makes sense to me if we're going to start somewhere and we're going to cover this, let's put it at the beginning. So as we're learning, like.
Well, and that's kind of, we've kind of gone over a lot of this.
Right.
So, except for review purposes, they just established the book that this is unit 17. It's kind of a starting, like, it doesn't make
Yeah.
sense. Start? No, it's dead. You got jumper break?
We got some 12 gauge wire over there.
That's what I just told my dad. I was like, well, you don't find any jumper cables. I got fucking 12-2 down in the basement.
You have to wrap it a couple of times.
Oh, you gotta wrap it once, get it through the feeder. I've done this a couple times. Yeah. I'm sorry. Can't you hear it? Even? We're gonna be turned on.
Where's she stranded at? Oh, she went back up.
Yeah, yes.
Well, let's get started again here. So what I was talking about was with the short is I've seen lots of motors when they start to fail, you'll start tripping one overload. You'll go and you measure the resistance off each coil and you'll see if there's a noticeable difference. You can even check a shorted winding out with a current. Just take an amp clamp and the one that's shorted will draw a lot more. And you'll definitely see an imbalance. And once you start seeing an imbalance, it's too big of a deal. You might as well just get rid of it. Get rid of it. So
That's how mine are, right? If it don't work, I break it.
yeah,
That's what it's like. All we really do is we'll test it and see if it works. If it doesn't work, we'll replace it.
yeah, especially like blower motors and small motors and stuff like that. There's no sense in even messing with them. Dime a dozen, anymore. Short circuit condition. A true short circuit condition across the heating element follows right here. So right here, it's showing us this super handy red wire is just jumping out the load. We will still have a circuit there, and there may even be some resistance in it, depending on where it is in the system, but that's clearly a short circuit right there. We're shorting the circuit around the load. Keep this picture in mind. Here's a tech tip. Do not test a transformer voltage using a spark method. The spark method involves quickly touching the 24-volt transformer leads to each other. This is from the book. And now I added my own 2 cents here that says, let's just use our meters, okay? Let's not do the spark test at all. Let's just use our meters. That's not a good practice. You never want to just be sparking sparks for the fun of it. If you're suspecting that you have a 24-volt transformer, kill the power to it, hook your leads up, and then plug it back in or turn it back on. Yeah, that's fine. We generated in our electromagnet lab the other day, Friday. We made electromagnets, and we generated almost up to 1 amp of current just from an electromagnet, and that's easily enough to kill you. And we were only using about 2 volts DC. Oh yeah, anytime you got a coil, that's a huge amount of inductance. Who's tasing you?
Sitting there giving me shit. She's like, you don't shut up, I'll tase you. It's like, do it.
So what he's saying is he didn't shut up and he got taken.
Okay, moving forward. Jason, we just got done talking about this tech tip. It says, do not test a transformer voltage using the spark method. The spark method involves quickly touching the 24-volt transformer leads to each other. That's what the book suggested. I'm going to suggest that let's just use our meters, okay? Let's not do that. Yeah, yep, it is. Let's not do that, all right? So I just want to know it. I want you guys to know this tech tip is very likely in your book.
It is.
Yeah.
I just read it.
Yeah.
The reason is they suggest not doing it.
Yeah. That's fine. That's fine to not to do it because you're going to blow a fuse. Let's just not do it because it's not real safe. Yeah. Spark indicates that there's some voltage at the output of the transformer. Some transformers have an internal or external fuse protection that will blow if this procedure is used. Let's just avoid it. Let's avoid it altogether. If you find a transformer that has an internal fuse and you're not getting an output voltage on it, what's one way that you can check? See if the fuse is blown. Yeah, just hook up to make sure that you actually have a winding for that side of the transformer, the secondary side of the transformer. Just go right to your 2 output wires, and you should see if you either have a close or you have an open. If you have an open, look for the fuse. So, yeah, ding-a-ling-a-ling. Okay, ground check. A ground circuit is similar to a short circuit. A ground circuit is one with the component where the component has less resistance than normal to ground. So in our case with the motor world, motors ground out. It happens. It's very similar to when a motor shorts out. It can short in the windings, or that same action could actually cause it to short to the frame. And our AC motors, the frame is on the coils are on the exterior of the motor, so that gives us the ground fault right there. Normal resistance to ground is called infinity, or at least it has a resistance of 1,000,000 ohms to ground. Maybe not always true depending on the situation, but it should be a very high amount. It should be quite high. And I can agree with this. If a motor winding resistance to ground is 100 ohms, this would be considered a grounded condition. I've seen motors be grounded when they're 1,000 ohms to ground. When you put a higher voltage to them or a higher current, they can ground out. All of this is relative to the voltage that you're putting through it. So keep that in mind. Here's an example of a heating element that's grounded. There will be some resistance to ground. Now I asked you guys to pay attention to this drawing. Do you see a ground fault there? I don't. What kind of fault do you see? A short? Yeah, so I wanted you guys to pay attention for this too. This particular drawing is showing what kind of fault. is showing the ground fault. What should it look like? Power supply. So if we were to actually have a ground fault, we wouldn't expect to see, we don't have a red. We wouldn't expect to see this, would we? No, heck no. That's a short. We're shorting out the load there. What we would expect to see in the motor's case is we would expect to see a little winding peel off and go to ground. That's what we would expect to see. This doesn't exist. It can exist if it's a real failure of the motor or the load. That definitely can be a part of it. But when, you think? I don't think it is.
Well, I didn't do it in the slideshow, they just put it in the demo.
I don't think it's going to show it on the next one. That's what I'm wanting you guys to see, is just make sure that it's actually a short to ground. So if you grab your meter, you stick it on this voltage here. Here's a meter point, and you take it over right here. Whoops, excuse me. That ain't right either. So you take your ohm meter out, switch it over to ohms, and you read from this over to this coil. You should have a very high resistance. But in the case of a ground fault, this will be, instead of going from 1 meg on the normal stance, in a normal stance being 1 meg, this will go from 1 k ohm, or even on a fluke meter, or even I think your guys' meter has the points. This will read down into just the 100 or, lower, significantly lower. You'll know. You'll be like, oh man, that seems like it's low. So, all right, moving forward. Yeah.
Well, it's at 17-1. It's supposed to be figure 17-1750. It's at 1714.
Yep.
It's looking around, like in the book, it has both.
Okay. All right. Well, way to go for having the book, my friend. So good on you. But no, I wanted. This is when I was prepping for this. I noticed this. I'm like, oh, whoa! I need to make sure that my guys realize that this is definitely not a ground fault case. This is a short. And what should a ground fault look like? So that's why we went over here for this.
Yeah.
Wiring diagrams and wiring schematics. Electrical diagrams may be called wiring diagrams, schematics, ladder diagrams, pictorial diagrams, external diagrams, connection diagrams, panel diagrams, or hookup diagrams. Wiring diagrams are also known as pictorial, external, hookup. Man, that is exactly the same thing that we just saw there. Okay. A wiring diagram is a snapshot or pictorial view of what a technician can expect to find when the equipment cover is removed from the HVAC235 system. Wiring diagram is arranged so the physical location of the components in the diagram is similar to the arrangement of the actual equipment. Figure 1711, the next slide, is a simplified pictorial diagram of a basic packaged air conditioning and heating system. We've spent some time with him already. Wiring diagrams. The features of the wiring diagram show 1716, the connection diagram, the list of components name, and the color code for the wiring. What's going on? We need some power or what? Do we need a cord? Let me see here. What number are we on? 51 of 102. You guys about tired of listening to this for the day? Yeah, I'm sure we all have. Let's see. What time do we get out of here? Oh, we only have till 3. Oh my goodness, I thought we had till later.
Okay, well, let's just pause with this here today. We're halfway through. The next half is going to be a little more difficult. We'll spend some time, maybe have you guys go through some drawings. What I want us to start with for our lab, I'll just push pause and let's give me a second here. Stop